So you 2 problem 6. Prove that any monic of degree n with real coefficients is the average of monic polynomial degree with n real roots. Right. So I'll just like write the problem here. So like you've been asked to prove that given any p of x in R of x, prove that there exists a comma b belong to R of x such that yeah, and p of x is monic. That is also given. Prove that such that a plus b equals to p and a comma b have degree n, have degree p and degree p number of real roots. Okay. So like to solve this problem, the problem asks us to like show the existence of two polynomials a and b, right? Such that they have both of them have like n number of real roots, but n is like degree p, and both of them have degree n, and they sum to twice the given polynomial p. So what we are going to do is like we will explicitly uh, build such polynomials a and b, right? So what one thing that we must keep in mind is like we have two conditions on a and b, uh, a and b, actually three. So like if we develop a, we will like simultaneously develop b as b equals 2p minus a. Another thing we need to keep in mind is like n real roots, right? And another is like monic. So these are three conditions that we like need to keep in mind, right? So first thing we know that whenever we are trying to construct a polynomial, Lagrange interpolation is like very helpful, because you can like given any values, like given the values it takes at say n plus one different points, you can like just construct a good polynomial and like be happy. So like Lagrange interpolation helps with constructing polynomials, right? And another thing we need to keep in mind is n real roots. So like how do we incorporate the sense of a real root while using say Lagrange's interpolation theorem, or in generally looking at function values at like say 2 points which do not seem really related at first glance. So like what we will do is like we will use
So
yes.
in the n plus 1 values, we can choose like n roots. Maybe that helps while constructing A.
No, like it does not, suppose you choose that like does not really give you like, if you choose A to be monic and have n roots, it's not necessary that B also has like a monic and has n real roots. So that's not that simple. Did you get what I was trying to
Yeah.
say? Like if you like just directly try to do that, like yeah,
Yeah.
so that does not work. So what we will do is like we will appeal to an intermediate value theorem. So like if someone does not know, intermediate value theorem says like if you have a polynomial f, right, and if you have 2 points a and b such that f into a, f of a into f of b is less than 0, then you will find an odd number of roots between a and b. What we are basically satisfied with is we'll find like at least one root, right? Because it kind of like changes sign and stuff, and it's continuous. So somewhere here it must hit a root, right? So this is really important, and so this basically tells us that if we uh, choose our values carefully, right, and say we choose the first value, the first function value to be such that the first one is positive and the second one is negative, and the next third one is positive, and so on. Right. So suppose we choose a sequence that in real numbers x1, x2, x3, xn plus 1, right? In such a way such that a of x1 equals a1. Now note that x1 up till xn plus 1, what we are choosing is like we haven't completely decided yet, right? So like we will choose it in a specific way, but let's keep the IVT idea in mind and proceed. Right. So suppose something happens like, suppose you have P of xi equals say yi, right? So first think of like say a of xi equals ai, right? So to first of all we need to ensure that a has like n real roots. So we will choose ai such that the IVT condition satisfies. Also like note that uh, uh, if you force A to be monic, then B ought to be automatically monic because you just define right. So for to for n is something like this, right? Greater than zero, then zero, then zero. So and suppose so like if you somewhat suppose x1, this is x, this is x, this is say, and this is xn. So like have a somewhere here negative and the root somewhere like
Aryan
you
is
end up
kind of breaking. Can you just
x
check your internet on?
root in x2 comma hello, is my voice audible now? Hello.
Yes.
Yeah, it's audible.
uh, okay, so like yeah, where was I? Yeah, so uh Yeah, so we like choose the function values of uh, ai of the polynomial ax in such a way such that like it has a root in between x1 comma x2 x2 comma x3, right, and so on xn comma xn plus 1. So it does have n real roots and we are happy, right? But does it finish? Because if we just do this, then we are not sure that uh, like a of x is monic, right? So like if we just go on with this construction, like uh, you just have a root in between this, and so on, right? Between any two consecutive xi, then you do have the thing that n is n roots, but you do not have monic. Like monic is not necessary. Excuse me. So like, how do we counter that? Anyone has any ideas? I'll just like tell you. So like, so what our problem was, like it feels like we have one variable like too short, right? Like it would have been a lot better if we had like n plus 2 variables, like so we could like also ensure uh, like n roots, and we would use the last one to ensure monopolynomial, right? But now like think of the matter once again. Why do we need the n plus 1? Like suppose this was xn and this was xn plus 1, right, and this was xn minus 1. So we have been told that there is some root in here, right? Now think about it. Do we really need xn plus 1, a root to lie between xn and xn plus 1? Like let xn plus 1 be anything. By choosing x1 till xn, we know that it has at least n minus 1 real roots, right? However, note that we also know that it is a degree n polynomial. So it can't happen like it has n minus 1 real roots and one complex root. That does not happen because complex roots like come in pairs, right? So it must have exactly n roots, notwithstanding what xn plus 1 is, right? And so we use xn plus 1, choose, okay, choose xn plus 1 such that it's monic, such that a of x is monic. Right. So this like helps us to like sort out the ax situation. The bx situation is like really the same thing. So you have like bx equals 2p of x minus a of x, right? So in that case, you have like b of bi equals 2ai, sorry, 2yi minus ai, 2yi minus ai. Right. Once again, like we will choose AI in such a way such that uh, 2yi, 2y1 minus a1 is less than 0, 2y1 minus and a1 is uh, okay. So just write is greater than a1 and a1 is greater than 0. 2y1, 2y2 minus a2 is greater than 0, or uh, 2y2 is greater than a2, and also a2 is less than 0, and so on. So once again, like by the previous argument, so in this way what we just ensured is like b1 is less than 0, b2 is greater than 0, and so on, right? So what happens is like once again, so b of x has n plus n minus 1, at least n minus 1 real roots by the previous argument. So it has exactly n roots. And also since a of x we chose in such a way that it was monic, we have like the leading coefficient of b of x is like 2 minus 1 basically, because p of x is also monic, so it's 2 times leading coefficient of p of x, that's 2, minus a of x, that's 1. So that yeah, so that finishes. Does anyone have any doubts regarding this? Does anyone have any questions regarding this?
Oh, how do we ensure there are only like there are currently n roots also, like between x1 and x2 there can be three roots also, no?
No, but if we like choose them in such a way, that is not a really big problem. Like you are choosing a1, like you are not just choosing like only one interval, right? You are choosing n intervals, and you ensure that there is one root like between each of one of them.
Oh, okay. So basically, like there are n interval and each should have a root, so there are one
Yeah,
only in each interval. Okay.
yeah. So that gives you like no, but you actually have like n minus one interval, so that gives you n minus one, and you get an extra root for kind of free, like because you cannot have a degree n polynomial with exactly n minus
Yeah.
because the complex root depends. Yeah. Okay, I will move on, I guess. So like the next thing I will talk about is
So also
differentiation.
in the
Yeah.
previous question, like suppose you are writing in an exam, so like does this suffice or we have to show that such AIs and BIs also exist?
Yeah, you could just say pick, like this is quite trivial basically. It does not require like because you pick any one greater than y1, right? And you pick it to be large enough such that it's greater than zero. You pick any a2 less than 2y2, and you pick it small enough to be less than zero. Nothing really you need to prove. Let's just say we pick ai appropriately again.
Okay.
So the next topic I wanted to discuss is like differentiation, right? So last class we used differentiation to like unwrap values while solving polynomial equations. Today we will use it for a more broader purpose. So like the first problem I want to show is problem 2. Yeah, Mason Soter's theorem. Okay, I'll just like uh, tell you the proof for this. Uh, Tell you the problem first. Okay, so like I will just introduce a notation that is called rad of a polynomial. We will use this in the solution a lot. So basically, suppose you factorize a number, right? Suppose you factorize, say, uh, a number n that is 2 to the 4 into 3 square into 5, right? When we say rad n, we mean the product of the distant prime divisors of n. So rad n for this is 2 into 3 into 5. Right. So similarly, we define for a polynomial p, we define rad p as product of its distant irreducible factors of its distant irreducible factors. Okay. So what Mason's-Noether's theorem tells you is Mason's-Noether's. So now, why am I covering this theorem is because the proof for this theorem is very instructive and it will like help you a lot. Like there are a lot of takeaways from how we prove this theorem, and it will help you like in solving some other problems. For example, uh, you can solve 3, 4, and 5 number questions 3, 4, and 5 using like what you learn from this proof of the theorem. So the theorem tells you that suppose a comma b comma c are like complex polynomials such that a plus b equals c, right? And GCD of ABC is 1, right? So you have to prove that maximum of their degrees is at most degree of rad ABC. Just less, I just write less, right? So does everyone like get the statement? So like if a plus b equals c and they are also relatively coprime, then prove that the maximum degree that they can have is still strictly lesser than the degree of the rad of their product, right? So like first thing what we will do is like we will first of all notice that for any uh, for any polynomial, f of x f by rad f must divide f comma f dash. So this is like you can just prove it for yourself. I'll just like let you prove for yourself.
What
So
is
like
f
how
dash?
f dash is derivative of f.
Derivative.
Okay. So like if f does not have any repeated factors, then it's just a constant polynomial. This thing, right? So a constant obviously divides anything. And if it has a number of repeated roots, then it still divides f. And if say alpha is a repeated root of f, right? Then x minus alpha is a factor of this thing, and you know that in that case f dash of alpha must also be zero because it's like well known, right? So now we jump to the proof, right? So firstly note that you have c equals a plus b and c dash equals a dash plus b dash by differentiating. Also recall that gcd of a comma p comma c equals 1. So this is an important condition and we will exploit this as much as we can, right? So firstly, you write C dash in two ways. So you can write this as C into A dash plus B dash, and you can also write this as C dash into A plus B, right? So what does this give you? Okay, yeah, A dash C plus B dash C equals A C dash plus B C dash. So you have A dash C minus A C dash equals B C dash minus B dash. So this is something, right? So like this is actually something to get you started with. So now note that okay, what we from what we did earlier, we know that if you have like c by rad c divides c comma c dash, so it also divides any not linear combination of c comma c dash, like linear as in c multiplied by any polynomial plus c dash multiplied by any other polynomial. So it must also divide uh, c by rad c divides. I'll just okay, just write the full thing. Rad c divides b c dash minus b dash, right? Similarly, you also have b by rad b divides b c dash minus c b dash, and also a by rad a divides a c dash minus c a dash, which is equal to b c dash minus c b dash, right? So like what is the takeaway from this? Also recall that ABC are all like relatively co-prime. Hence, if you like take rad of A into rad of B into rad of C, since they do not share any common prime factor, it's equal to rad ABC. So what I'm saying is like rad A into rad B into rad C equals rad of ABC because no common factors from the GCD condition. So what we understand is like we can basically combine all the three divisibilities and write ABC by rad ABC divides say b c dash minus cb dash. Now think about this. What is the degree of this thing? The degree of this thing is like degree ABC minus degree rad ABC, which is say greater than degree ABC minus degree A, and this is obviously greater than degree of BC dash minus CB dash. I mean, you can just like check for yourself that the degree of this big thing is like must be bigger, strictly larger than the degree of BC dash minus CB dash. Now, like if you have a higher degree polynomial always dividing a lower degree polynomial, it can only happen that the lower degree polynomial is zero, right? So like if because if you have like a higher degree polynomial, it grows like way too large than the lower degree at larger values, so the divisibility simply can't hold. So the only possibility is bc dash equals to cb dash. Now think about it once again. What does this imply? You know that b comma c cannot have any uh, factors in common, right? Because they have like a GCD of one, right? So this again must imply that c must divide. Now note that like c divides b c dash, right? But you but we just noticed that C and B cannot have any factors in common. So like this implies that C divides C dash. But then again, that means that C dash equals to zero by the same argument, because like C dash has a lower degree than C. So yeah, this presents a problem. So yeah, we are done basically. Like the like we assume contradiction, and like this basically does it. Does anyone have any questions?
What did we contradict? Like, what was our assumption?
Oh, like I went a bit hurriedly through it again. Like we assumed that this does not hold. So we assumed like say degree A is greater than degree rad ABC if possible, and then we contradicted it.
So, like, the contradiction was way earlier. This one you just gave a result, right?
I didn't get you.
Can you go to the next slide? Ah,
Yeah.
okay. Yeah. So, like, the contradiction was at the uh, third line only, no? Like, you do get degree of A.
Yeah, we use the contradiction assumption here, and then like to prove degree BC dash minus CC dash, because like the this argument pulls through because of what we assumed in contradiction. Do you get the point?
Yes.
I'll just go over it real quick. So what we assume is like the theorem is false at degree, say if possible, degree of A is greater than degree of rat ABC, right? Then we basically interpret C dash in two different ways and get this result, right? And then like we use divisibilities. Like we know that C by rat C must divide C comma C dash, so it divides this thing. Similarly, B by rad B must divide this thing. Similarly, A by rad A divides this thing, which is equal to this, right? This thing, which is equal to the other one. So basically, we find out that uh, ABC into rad A into rad B into rad C divides the entire thing, but they have no common factors. So you see, like rad A into rad B into rad C equals rad of ABC, right? And now you just degree bound to get that this thing must have degree more than ABC, must have degree more than BC dash minus CB dash, right? And then like from there it's easy, because like if this bounding part is quite easy, and like if the bound holds, you get that this is a higher degree polynomial than this, so this must be identically zero. In that case you have like bc dash equals cb dash, so c must divide bc dash, but again you know that b and c cannot have any factors in common, right? So c must divide c dash, which again higher degree polynomial divides lower degree poly, so that again like gives you c dash must be zero. So that is another problem. So basically c must be constant, and similarly you can get the others are also constant. Yeah, and that is a contradiction. Yeah, ABC were obviously non-constant. Is that clear? Anyone else have any questions? Okay, then I will move to the next problem. Uh, I'll just read it out. Okay, let for a polynomial f, let s of f denote a set of distant real roots. Set of distant real roots of f, right? Does there exist p comma q belongs to real, which is like just p and q, such that uh, s of p equals s of q, and s of p plus 1 divides equals s of q plus 1. Okay, is the question clear? Like basically it's telling you that if S of f is denotes the set of the distant real roots of f, right? So the question is, does there exist two polynomials p and q such that s of p equals s of q and s of p plus 1 equals s of q plus 1? Actually, like, the answer to this question is no, right? And we will do this now. So first of all, like, let us write p equals, say both of them have like, okay, I'm not even interested about degree. So like, suppose the number of distinct, suppose this set has cardinality n and this set has cardinality m, right? So you can write something like uh, uh, p equals summation, sorry, multiplication of I equals 1 to n, x minus alpha I to some exponent, say ei, right? And q equals to summation of I into this to the ei dash, right? And suppose you can also write p plus 1 equals to okay, suppose I equals 1 to m x minus beta I into ei, not ei, say fi, and q plus 1, sorry, equals I equals 1 to m x minus beta I to the fi dash, where all the alpha I and the beta I are different, right? So like, first thing we can do is like, so like, one thing you note, like, both p and p plus 1 share the same derivative, right? And p and p plus 1 cannot have, uh, excuse me, and p plus 1 cannot have any root in common, because like they're separated by n, right? So like, once again, if we like take the derivative of p and p dash, p and p plus 1, right? So on one hand you have something like x minus alpha, so multiplication of this must divide, just by taking the derivative of p, you know that multiplication of this minus 1 must divide p dash. And similarly, taking a derivative of this, you know that multiplication of x minus beta I to the fi minus 1 must divide p dash, right? Also note that the summation of all the ei is equal to degree p, and the summation of all the fi is equal to degree q, right? Also, we are like working in complex numbers, so like everything is factorizable, and so on, right? So this basically tells you that, also note that since alpha and beta are all distant, you can basically combine the two divisibilities, right? So you can write multiplication of x minus alpha I to the ei minus 1, and summation and multiplication of x minus beta j to the fj minus 1 divides b dash. So what this tells you is that basically this gives you a this gives you a inequality, right? So like, if you just interpret in terms of degree, this tells you that the first equation has like degree p minus n. The first factor is like a degree of degree p minus n. The second factor has a degree of degree p minus m, and this is like at most degree of p dash, which is degree p minus 1, right? So this quickly gives you an inequality degree p is at most m plus n minus 1. Similarly, degree q is also at most m plus n minus 1, right? So now what we do is like, we try to establish like another inequality such that this gets contradicted somehow, right? So also like, note that uh, multiplication of x minus alpha I divides both p and q, right? So it must divide p minus q. So this thing divides p minus q, right? So like, also you have something like x minus beta I must divide p plus 1 and q plus 1. So it must also divide their difference, that is p minus q. Once again, we have like two factors of p minus q. Uh, right, okay, let me go to the next page. So you have something like x minus alpha I product and x minus beta I product is a divisor of p minus q and uh, p plus 1 minus q minus 1. Now, if this polynomial is not 0, then what happens? This has like n factors, this has like m factors. So the degree of this thing is n plus 1, right? And this must be at most the degree, the maximum degree of p and q. Degree, okay, right, max first. Max degree p comma degree q, but by the previous equality it's like at most m plus n minus 1, so you get something like m plus n is at most m plus n minus 1, so that obviously can't happen, so we arrive at a contradiction. Okay, so anyone have any queries regarding this finishes the problem. Anyone has any questions regarding this?
Can you go over again once again about that inequality where you got maximum of degree p comma degree q is less than equal to m plus n minus 1?
Okay, like, do you agree with the fact that if you just like that this holds, right, what is it, yeah, I'll just clean it up. Do you agree with the fact that this holds the black box?
Yes. Yes.
Right. So this, okay, and you also note that this holds because we are just differentiating p plus 1, right? So now p and p plus 1 cannot have any roots in common, right? Because they are like separated by 1, right? So you must have like alpha I and beta I are completely distant, right? So you have like two coprime factors dividing p dash, so you can like combine them, right? So you can write product of x minus alpha I to the e minus ei minus 1 into product of x minus beta I to the fi minus 1 divides p dash. Now if you like look at degrees of both sides, the degree of this thing is, note that summation of all the ei's is what? Degree p, right? So you are some like summing up all the ei's, summing up all the ei minus 1. So sum of all the ei is like what? N, sorry, degree p, and there are n number of ei. So that's degree p minus n, right? And similarly, the other term is degree p minus m. M was like the number of distinct roots of p plus 1 and q plus 1. And you know that their degree must be at most the degree of p dash, which is p minus 1. Yeah, so that gives you the inequality.
Okay, I understood.
Okay. Any more questions? So then I'll like move on. Okay, I'll just move on then. The next thing I want to talk about is size, I think. Yeah, okay. So the next thing I want to talk about is like somewhat like analysis arguments or like growth rates. So like what I mean by analysis arguments is like the only thing basically you need to understand is like a polynomial grows very slowly with respect to an exponential. So like for any like exponential function, it would eventually dominate a polynomial function in terms of its growth. Another thing uh, is like any polynomial p of x with leading coefficient x to the n, right? Like it so happens like p of x tends to ax to the n for some large a, or not for some large a, for some a, and large enough x. So any polynomial of degree n like grows like x to the n polynomial for large enough x, right? And also for like uh, for sufficiently large x, right? Suppose the leading coefficient was an and any real number k, right? You would get a point such that this inequality always holds. So these tidbits are kind of necessary, and this like keep on reappearing in like problems. So I like solve two problems, which like just highlight
Can you tell
some.
again this? Inequality, I couldn't get it.
Yeah, this holds like for any large enough polynomial. So, not large enough polynomial, for any polynomial and any real k and for large enough n.
What is an and k?
An is the leading coefficient, like coefficient of x to the n, and k is like any real number.
Okay. And that capital A is equal to an plus k basically.
Not really. Capital A can be something like the product of, no, not product, say the uh, sum of absolute values of the coefficient, right? Like some- by this sign, I might mean something like, uh, how do I explain this better? Like you can find constants such that c1 into x to the n is px is greater than this and greater than this. So basically, in notation wise, you can say that it grows as theta of x to the n if you know asymptotic notation.
Yeah, okay, got it.
Okay, so like I'll move on to a problem, right? This is
Basically, it's like O of x to the power n, right?
yeah, yeah, exactly, yeah. Okay, let's do problem two, and I plan to do problem three as well. Uh, okay, so this problem tells you, does there exist an infinite sequence of xi, yi, where I is at least like where they range overall like xi and yi, which is the infinite sequence, such that for any real sequence, excuse me, bi, you have there exists a polynomial pxy belongs to rx r adjoint xy, such that r of sorry p of uh, p of xi comma yi equals pi. Right. So is the statement clear? Basically, it tells you whether there exists some sequence xi and y xi comma yi, right? Like a sequence of pairs of xi comma yi, such that for any real sequence, right, there exists a polynomial such that this holds. So like when you first see the problem, your gut reaction should be something like there does not exist. Because like the first thing you think of is like if bi like increases too fast, then the polynomial won't be eventually able to catch up with it in a way. Like you can't have something like bi is exponential, right? Then you have a problem. Like this intuition is enough like to solve the problem. First, like note that if the sequence xi comma yi, firstly it must be unbounded, right? Because if it's like bounded, then you just pick bi to be any unbounded sequence. Then you can't ever have something like the polynomial values obtained by a bounded sequence is unbounded. That's not possible, right? So first thing, the xi comma yi must be unbounded, right? So now we choose like just take something like bi equals e to the ci. What is ci we will determine later, so that it meets our purposes. So now we will just use stupid bounds, right? So like suppose uh, say the degree of, suppose such a polynomial p exists for bi equals 0 to the ci, and suppose the degree of px comma y is let's say d. Right. So now note that any polynomial of any, like it has a lot of terms of the form say x sub k and y. Okay. Now when you like write the polynomial, it will have terms of the form xi to the k and y to the l, yi to the l, and so on. Right. So now what we can do is sort of, excuse me, like if you just like use triangle inequality on it and bound it, right, you get something like it's obviously say max. Uh, you can use this like easy bound and k plus l is also like at most d. So so like for every polynomial, like not polynomial, for every term of the uh, for every term of uh, p of x comma y, you can use estimates of this form, right? And like if like also note that if the xi to the k and yi to the l coefficient was like say uh, a, right, then you can also have like a mod a value here. So this basically tells you that if you use this kind of bound, right, so then mod of pi comma xi must be at most sum of uh, a constant value s, where s is like sum of absolute values of all coefficients, just like we did here, uh, of all into mod xi. Let's say the max of this is xi, say, right? So you get like it's at most s times mod xi by to the d, right? So now you also know that we had to now we choose bi like wisely. So basically just choose bi equals e to the xi, uh, right? So is e to the x, yeah, that just works, I think. uh, yeah, that just works. So like now you would want to have like something like e to the xi is greater than x, e to the mod xi, sorry, e to the mod xi is greater than. So now for large enough xi, because xi was bounded, you would have that this inequality hold, so the problem statement cannot be satisfied. uh, do you
Where did S come from?
Oh, S is like, okay, so like suppose you have a term of the form xi to the k and yi to the l, right? Then you can just use this kind of bounds. These are like easy bounds, right? Now suppose it had a coefficient with it, so you can like also take mod of the coefficient inside this bounding, right? So like if you have terms of the form like 5x cube y to the 5 plus say 2x to the 3 y to the 7 and so on, like you can also like take some absolute values of all the coefficients and sum them up to get the bound, right? That's exactly what we're doing. So like I'm just showing an example, concrete example on the next page. Suppose you have the polynomial like 5x to the 3 y to the 7 plus 9 x to the 4 y to the 10 and minus uh, 3 x to the x y to the 2, right? So the degree of this thing is 14. So what we will do is we will bound this term by 5 to the let's say this is actually x and y are fixed here, right? So suppose mod x is more than mod y. Suppose if mod x is more than mod y, so you just do this plus y to the 14 is supposed to be x, yeah, plus 3 times mod x to the 3. So basically this is basically what we are doing. So this becomes mod 5 plus mod 9 plus mod 3 into
Uh, shouldn't the last term be 14? Yeah.
yeah, I corrected it. Yeah, this is basically what we are doing. So like it's not really essential, you can just take something more than x. Basically what is a matter, like what we care is like basically it's less than constant times of mod x to the mod xi to the d for some large enough constant. But if we like just take it to be exponential, then basically we want an inequality of the form this to hold, but this can't hold for like large values of x, like, right? Get the point?
Yeah. Yeah, got it.
Okay, okay. Cool. So that was one. If anyone has any other questions, please ask. If not, I will move on to the next problem.
How does the intuition develops of using these ideas? like which you are using in these questions?
In particular, this problem, it was like,
No, like the questions which you covered since yesterday, like overall, like all
yeah,
of these ideas are new.
you like solve more problems, you develop more ideas. That's really how it works. Like, you solve a bunch of problems, you gather ideas. You like, might happen, you solve a you take a new problem, you don't have any progress on it, but like, if someone gives you hints, or like you get hints from somewhere and like you solve the problem, then you develop a new idea, or you see a new idea, new intuition. Basically, that's how it works. Nothing else really.
Yeah, okay. Thanks.
Can you suggest a book which you used for for the practice, for your practice?
For practice, like, there's not really any book I ever use. Like, for theory, you can like check the handout I posted in resource share channel yesterday. That
I
quite
checked it out.
Yeah, and it has a lot of problems. Do them, and like, you can just check contest collections from Europe. Like, you can do Iran. Russia has a lot of problems. Iran has a lot of nice polynomial problems, and there's like ISL always. Yeah, that's about it. That gives you enough practice. And international contests also, check them out.
Because at the first glance, this seems very abstract. So it is not very easy to directly get
It
into.
like get better with time. Like, uh, yeah, it just need a bit of practice. You can like try the problems I sent in the problem set as well. Quite a few good ones. Okay, I'll move on to the next problem.
Okay.
Okay. Okay, so like for this problem, we will use Cauchy's mean value theorem. I'll just like leave the statement up for it. Cauchy mean value theorem. So Cauchy mean value theorem tells you that if f and g are so suppose f and g take an interval to real are functions from an interval to real numbers, be continuous functions, and differentiable on comma b with fa not equal to fb, and such that f dash c is not equals to 0 for all c in the interval, right? Then there exists c belong to a comma b, such that uh, gb minus ga by fb minus fa plus g dash c by f dash c. So yeah, this is basically the theorem. It tells you that if you have like two functions taking an interval to real numbers, which are, you need three requirements. It is continuous on a comma b, on a comma b. It is differentiable on a comma p, and finally fa is not equal to fp. F dash x does not vanish on a comma b open. Right, then this holds. This relation holds. So there exists some c such that gb minus j by fb minus fa is equals to g dash c minus f dash c for some c in the interval. Right. So like, knowing this, let's try this problem. So what does it say? So f comma g are quadratic real polynomials such that f of x belongs to z implies, so whenever f of x is an integer, g of x is also an integer, right? Prove that there exists a comma b integers such that g of x equals a f of x plus b. Okay, so how do we solve this problem? So first of all, like, we will so first of all, like, to start off with, assume that f and c have like positive leading coefficient. F comma g have positive leading coefficient. If not, just like swap, excuse me, f for f, minus f, and g for minus g, right? So like, first of all, like, this is a kind of formality. So like since they are like both positive coefficient, positive leading coefficient, after the point both of them will be increasing, right? So choose large m such that like f and g are increasing in m comma infinity, right? And for now, note that since it's a continuous function, it basically covers anything in m comma in fm comma infinity, right? So like for large enough positive integers n, consider the sequence xn such that f of xn is equal to uh, n, right? Just because of continuity, this holds, right? There exists xn such that for every n you have for every n large enough, you have f of xn equals n. So now, by the problem statement, since f of xn is an integer, you must have g of xn equals to say gn is also an integer, right? So now, think about the how xn actually grows. So note that as n grows very large, xn must also grow very large, right? Because of the positive leading coefficient thing. And similarly, as xn grows large, gn must also grow large. So what we will do is we will apply Cauchy mean value theorem on xn comma xn plus 1, right? So if you just directly apply this, what does it give you? So there exists some, so this gives you that there exists some cn in xn comma xn plus 1 such that g of xn plus 1 minus g of xn divides f of xn plus 1 minus f of xn. That's just n plus 1 minus n, that's 1, right? Equals to g dash cn by f dash cn, right? Or in other words, just write it in a better way. Okay, right. So like also note that as xn goes to infinity, that is when n goes to infinity, cn must also go to infinity because it is sandwiched between xn and xn plus 1, right? So now think about this term. What happens? What is the limit of this term as n goes to infinity? So like suppose g of x, sorry, g of x was something like ax squared plus let's start this with b. Suppose bx squared plus stuff I don't care about, right? And f of x was ax squared plus again stuff I don't care about. So g of x is something like 2ax plus 2bx plus constant term, and f dash x is like 2ax plus constant term, right? So like when you take n tends to infinity, if you know how to like do limits, then this basically equals b by a, right? So like when n tends to infinity, this fraction value equals b by a when b and a are like the leading coefficients of gn. uh, f and a are like, sorry, b and a are like the leading coefficients of g and f, right? Also like note that b by a must be an integer because of the fact that this value is an integer, right? This is equals to gn plus 1 minus gn, right? So this basically tells us for all uh, for all large n, gn plus 1 minus gn equals b by a, right? But you can also write this as b by a into 1, which is basically n plus 1 minus n, which is this, right? So now basically it's, we are done basically from here. So like you can write this as g of n plus 1 minus b by a f of xn plus 1 equals to g of n minus ba into f of xn for all large enough n. So this basically tells you that the polynomial g of x minus b by a into f of x has like uh, infinitely many roots. Like it's the same value for like all large enough n, right? So for all large enough like xn. So this basically tells you that this must be a constant c. Yeah, and that concludes. Yeah, anyone has any questions from this? Anyone has any questions, please feel free to ask.
We have assumed f of x of n equals n, right?
Yeah, we assume so. Okay, if there aren't any more questions, I'll just move on to the next part, which is like two variable polynomial or like homogeneous. Okay, just multivariable. The main thing, okay, the main thing I want to cover in two variable polynomial is like homogeneousity. So what is a homogeneous polynomial? A homogeneous polynomial is something like, just let's just do it in two variables for now. Is like, suppose you are, it's of the form a m comma n, where mn is a coefficient and x to the m y to the n, right? If m plus n is always constant, then it's called homogeneous. So something like, if you have fx comma y as uh, x to the 6 y cube plus x to the 4 y to the 5 plus x y to the 8, this is a homogeneous polynomial. uh, yeah, so this is a homogeneous polynomial, right? And suppose if you have something like x y, like this plus x to the 4y, so this is not homogeneous, right? So what is good about a homogeneous polynomial? So if say a homogeneous, the common degree of the homogeneous polynomial is the constant value m plus n. So like this polynomial has degree 6 plus 3, that's 9, right? And okay, so like if homogeneous polynomial say f of x comma y has degree say d, right? Then this holds, and this is basically the most important thing you need to know. For any real number, for any t, you have f of tx comma ty equals t to the d fx, sorry, t to the d into uh, f of x comma y, right? So this is the most important part of homogeneous poly, and this is the only thing you will need basically, right? uh, Another important fact is, okay, just give me a minute. uh, okay, so yeah, so how we will use this, right? So suppose you've been given a homogeneous, okay, did I unmute myself? Yeah, suppose you have been given a homogeneous polynomial x comma y, right? So what we will do is we will treat uh, t equals y, right? So what we will do is like, we'll like basically extract the y out of this and write this as px comma y comma 1. Do you understand what I am doing? So basically what we will, to like ease our purposes, we will write px comma y as this. Now note that this thing is a single variable polynomial, right? So we, so like using a method like this, we can transform sort of a two variable polynomial into a one variable polynomial, and this is like very important. Also another thing you must know is something like, any polynomial uh, p of x can be of degree n, can be written as a sum of homogeneous polynomials of degree k for all k at most n. So basically it's telling you that you can write p equals to summation pi, I equals to 1 to degree p, where pi are homogeneous polynomial. So this is called these are called homogeneous counterparts of p, right? So often in problems you would like need to do analysis on homogeneous counterparts and try to solve the problem. So that is also essential to know. My handwriting is getting worse with every passing slide. That okay. So like let's do a problem to. Anyone has any doubts with what I just said?
In the previous part, you said that we can substitute x or y with some another variable, but won't the behavior of these two polynomials be different because x and y are different?
I didn't really get you. Like the main property is that if you have something like you are like saying f of tx comma ty is equal to t to the t. So basically you can like take out the
No, no,
t
I
from.
understood that. When you said that we can substitute x or y with some another variable, so the polynomial which we are getting now and the earlier polynomial, their behaviors will be different because x and y are
be-
dependent on each other.
Behaviors in what sense? No, x and y are free variables, like they are not related to each other in any way.
Okay, okay. I thought like in a
So,
space it will be fine.
so something like if you just take the example of this polynomial, right? If you take y to the 9 out of this, what remains? Y to the 9 into x by y whole to the 6 plus what? X by y whole to the 4.
Okay, if they are free variables, I am not having any doubt.
Okay. Yeah, so this is basically the one variable polynomial in x by y I was talking about. Okay, let's move to a problem. So the problem is find all homogeneous poly pxy such that p of x comma x plus y plus p of y comma x comma y equals 0. Okay. Yeah, so this is the question. So find all homogeneous polynomials p of x such that p of x comma x plus y plus p of y comma x plus y equals to 0. So I'll just give you a warning. This is not a very good solution. So why I chose this problem is just like how to deal with this stuff, right? So what we do is first of all we take x plus y to the d common, right? Let d be the degree of p, and let's take p of like x plus y to the d common. Then what you get is something like x by so this, right? P of y by y plus d y plus x comma 1 equals to 0, right? So now note that as we said earlier, this thing is a one variable polynomial, right? So let p of x comma 1 be q of x, right? So what this basically tells you is q of x by x plus y and plus q of y by y plus y x plus y equals 1, right? So now note that basically this and this sum to 1, right? So in other words, we are just telling you that q of t
Shouldn't
plus
it be
q
equal
of,
to 0?
oh yeah, it's sorry, equals to 0, right? So like if you just like shift t to t plus half, then that basically tells you q of equals to minus q of half minus t. Is that it? Okay. Oops. 1 second. Okay, yeah. So now if you like let uh, this value, sorry, this polynomial be r of t, suppose, right? So if and then if you like rewrite the condition, this becomes r of t equals minus r of minus t, right? So now what does this imply? Like this basically tells you that r of x is an odd polynomial, right? And if any odd polynomial can be basically written as x, so r of x equals x into sx squared for some polynomial s. So this is basically well known. You can like prove it yourself. Basically, any odd polynomial can only have like x to the odd coefficient, right? And from here, it's like quite easy. Like, so basically you get something like q of t equals t minus half times s of t square minus t plus 1 by 4. And from here you can like basically solve it yourself. Like, it's just plug some values, like just plug this into the original equation and it becomes much more man like you can manipulate it much easier, and this basically gives you the solution. If you like just want a final solution, basically the main part of the problem was doing the homogeneity step, like taking out the excess y and then like uh, doing the transformations. So basically finally you would have a solution of the form after like expanding and stuff, something like this. Yeah, so this is the final solution. Like, you'd have something like p of x comma y equals to this thing, where g of x is a polynomial in degree d minus 1 by 2. Yeah. I'm guessing no one has any problems with that. This wasn't really a very hard problem with like any deep concept.
How do we specify G there?
You just like
Aryan, you're not audible. Guys, he said that he got disconnected and that he'll be back. Okay, he's back.
uh, just, yeah, basically my tablet just froze and it won't work. Okay, yeah.
Okay, guys, it happened again. Really sorry about this. He said that he'll be back in a minute. Really sorry about this.
Hello, am I audible?
Yeah.
Okay. My tablet crashed twice in like a space of 3 minutes. Yeah, let me share. Okay, 1 second. Yeah, for some reason it's still like quite slow. I don't know why. Uh, okay. Yeah, let me share. Yeah, is the screen visible? Is the screen visible?
Yeah, it
Yes.
is.
Okay, so like g of x was basically just you instead of s of this. Oh my God, the screen does not work. Instead of s of t squared minus t plus 1 by 4, you write that as g of t squared minus t, right? For some reason, the Jamboard doesn't work. But do you get the definition of g? You have something like s of t squared minus t plus 1 by 4, right? You basically define that as g of t squared minus t. Okay, uh, let me open just another software. I just plan to cover one more problem. I'll just open another software. Yeah, is the screen visible now?
Yes.
Okay, yeah, finally it works. Okay, so like I just want to cover one concept and one more concept and one problem. So like in a polynomial p of like n variable polynomial, say p of x1, x2 up till xn, right? If it so happens like p of x1 comma x1 comma dot 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 is 0, right? For all values of x1 or infinitely many values of x1, then you have something like x2 minus x1 divides p of, right? So this is basically factor theorem, but with more variables. So we will use this concept to like solve one problem. This is basically the last problem we plan to do today. So this is JMO 2026.
Oh, can
This
you tell
tells you
what did you say? Like what this?
like if a polynomial vanishes, if you have two of the values equal, two of the values of the variables equal, then that is a factor. Like like if you have something like a polynomial p of x1 comma x2 comma x3 up till xn, right? I mean a polynomial in those variables. And if you set x2 equals x1 and the polynomial gives a value of 0, right, for all other values of the other variables, then x2 minus x1 is a factor of p of the thing here. Okay, the problem I'm going to solve is like JMO 2026 that tells you that if p of x1, x2 up till xn is a non-constant n variable polynomial with real coefficients. Okay, so assume that p vanishes whenever two of its arguments are equal. Arguments are x1, x2 dot dot. Of its arguments are equal. Prove that p of x has at least n factorial terms. Right. So do you get the statement of the problem? Then I'll like move on to the solution. Anyone has any question with the statement? It's been given that a n variable polynomial like gives zero whenever two of its variables are like equal, right? And prove that it has at least n factorial terms, right? So first of all, note that for any like so by what we just discussed, you have like xi minus xj must divide p of x1, x2, so on, right? For all values of I and j, right? So now, okay, so like there are two solutions basically. One of them is like uses the Vandermonde determinant, right? And the other one is more low profile and it basically just uses induction and understanding of how n variable polynomial works. I initially intended to do the Vandermonde solution, but I think since we are doing n variable polynomial now, I will do the other solution, which is like just requires understanding of the n variable solution, right? So first of all, note that consider, so suppose you take the polynomial, right? And what happens if you like give one of them zero, right? Like place zero in one of the values, right? So like you basically delete all the terms having okay, so basically plug x1 equals to 0, say, like, right. So like basically in other words, you delete all the terms having x1. First of all, note that if like x1 divides p, you can just divide it out, right? And in the, yeah, you can just like divide it out and induct on the degree. So that is one way. I mean that, so you can just assume that x1 does not divide p, right? So now suppose you uh, like give like set x2 equals to 0 as well. So like basically set x1 equals x2 equals 0. So it is now a polynomial is something like p 0 comma 0 and you have like n minus 2 other arguments, right? So by the statement of the problem, this is always 0, right? So basically this is always 0. So like in other words, you can think of it like if you think of it in terms of an n minus 2 variable polynomial, right? Like if you say this is equal to r of x3 x4 up till xn minus 2, where xn like sorry not xn minus 2 xn, where this is an n minus 2 variable polynomial, then like note that this is 0 for infinitely many values of x3 x4 the n minus 2 tuple, so this is always 0, right? In other words, what I am trying to say is when does this like polynomial become like 0? When like every like when okay, this is difficult to explain a bit. So like suppose you write uh, this write p as something like okay, so write p as something like r of uh, x3 x4 xn minus 1 plus the rest. So basically, you write the polynomial as as two parts, right? The first part is the terms which do not have both x1 and x2. So like r of x3 comma x4 comma up till xn is like those terms which do not have either x1 or x2. So they do not have x1 or x2. And the rest of the terms which have at least one of x1 or x2 as a factor, right? So when you set x1 equals to x2 equals to 0, this part vanishes, right? So this goes to 0, right? This part vanishes. And by the condition of the problem, you know that this is also 0. So the other part, which consists of only x3, x4 up till xn as their coefficients, no, not coefficient variables, and do not have x1 and x2, this also has to be 0 because this goes to 0 and this is also 0. And this polynomial, you can think of it as a polynomial, must goes to 0, must be 0, right? So in other words, every term of of the polynomial p, like, must include, like, cannot omit, like, two variables at once. Like, for any two variables xi and xj, you cannot have a term, there does not exist a term omitting both. Like, you cannot have a term of the form, say, if it's a five variable polynomial, you cannot have something like x3 x4 x5. This is like the really the most important claim of the problem, right? Because, like, this kind of issue occurs, right? So having known this, we now, like, try to like, sort of induct, right? So as I said, like, we proceed by induction on n, right? Like, also note that if x1 say divides p, you can just divide out x1, right? So now let us look at p of 0 comma x2 comma x3 up till xn. uh, by the hypothesis, we assume x1 does not divide p. So this is a non-zero polynomial, right? But it also satisfies, so also note that it's like, satisfies the inductive hypothesis. Like, the inductive hypothesis is like, set two of them equals to 0 and they give 0, right? Satisfies ih, and also uh, it's not identically 0, right? So by the inductive hypothesis, this must have n minus 1 factorial terms, right? So similarly, basically, uh, there are n minus 1 factorial terms at least which do not have x1, right? Also, similarly, if you do something like x1, keep x1 at its place, give x2 0, and look at x3 up till xn, right? Then again, like, this polynomial also satisfies the IH, the inductive hypothesis, and also not identically 0. So also this gives you n minus 1 factorial terms, and you can do it for all the other terms, right? So this gives you at least a total of n minus 1 factorial into n times, n for every variable. So yeah, that gives you n factorial terms at least. Yeah, does everyone get the proof for this?
Oh, can you tell how did you get n minus 1 factorial thing?
We are using inductive hypothesis. Like, the problem is for n variables, right? We're inducting on the number of variables. So, like, if you, like, look at p of 0 comma x2 x3 up till xn, it's a n minus 1 variable polynomial, and it only consists of the term that do not have x1, right? So even in this polynomial, if you, like, uh, just, let's say, do x3 equals to x4, right, then it's still 0, and it's an n minus 1 variable polynomial, and it satisfies the condition that if you set two of the arguments equal, then it gives 0, right? Excuse me. So yeah, it must have n minus 1 factorial terms by inductive hypothesis. Similarly for the other terms, yeah, and you're done. And sum them up and you're done.
Oh, but like in that p of 0 comma x2 x3 so on till xn, if you put any one as 0, like suppose you put x2 as 0, then you get the polynomial is 0, right?
Yeah,
But
that's what we did. Yeah,
yeah,
that's what
but
we
we
did
will
here.
want, but for induction we will want that if you put x2 and x3 as 0, then only p becomes
Okay,
0.
no, okay. Let me explain this way. So suppose it's a 3-degree polynomial, and p of x1, x2, x3 is uh what x1 x2 plus x2 x3 plus x3 x1. This does not satisfy the condition, but let's just say this is the polynomial, right? So what is p of 0 comma x2 comma x3? It is what uh what is it? Yeah.
x2
So it's
x3.
basically just x2 x3, right? So now x2 x3 is a polynomial in x2 and x3, right? And it is a 3 minus 1 degree polynomial, and it also satisfies the condition. I mean, this does not satisfy, but the problem must satisfy the condition that if x2 equals to x3, then this polynomial becomes 0, right? Do you get the point?
Uh, yes.
Okay, feel free to ask if you just didn't get it.
Oh wait, but for all x2 equal to x3 won't we know? x2 equal to x3 equal to 0 was the condition, right?
No. The condition was just x2 equals x.
Yes,
not
so but
both zero,
in
not
in
both
this,
general. Like
yeah.
you can have something like if the resulting polynomial is x2 x3, and r of x2 comma x3 equals to something. If you just put r of 5 comma 5, that's also zero. It's
Okay, this
not
doesn't work. Right, so
okay. Yeah, yeah. Any other questions? Yeah, we will wrap this up. No, I did not plan to cover anything else. Any other questions from this problem or like in general from the lecture of both days?
I'll stop recording then.
Yeah, sure.